On board now, Dr. Jim White from the University of Colorado. Let's take a look live outside if we can, and I'll go through the introduction for Jim. Jim has been with the Weather and Climate Summit for the last 27 years. This is our 27th year for the Weather and Climate Summit, and we renamed it 3 years ago in honor of Glenn Gerberg. Jim is an integral part of that founding member and annual planning team, and he's with the University of Colorado. As the director of the Institute of Alpine and Arctic Research, Jim's climate research has concentrated on the global carbon cycle, reconstructing the climate record through the study of ice cores in Greenland, and he's focused this research and its findings to help answer the burning question from people around the world: what, if any, are the human impacts of our Earth's climate change? Jim teaches college students at the University of Colorado about environmental studies, the carbon cycle, energy and climate change, and today he'll teach us about abrupt climate change and what we're learning from his research in Greenland. It's not just research anymore. Greenland is a major contributor to sea level rise. So let's hear from Jim as a past speaker of the Weather and Climate Summit and a current speaker of the Weather and Climate Summit. Let's take a look at a brief video introducing Jim.
As a climate scientist, I do my work in Greenland and Antarctica because that's where the big ice sheets are. And we're seeing profound changes there. We're seeing melting of these large glaciers. I can tell you that big field work in Greenland, oddly enough, requires it to be very cold because our ice is our archive, and so if it's not very cold, we lose our archive. And we've had to adjust over the last 20 years to the fact that it gets warmer and warmer in the summertime. We have trouble flying planes in and out because the snow gets too warm and melty and sticky. We have trouble doing our ice core processing. We have to dig down into the snow to do all that stuff. So oddly enough, we need to keep it cold in order to keep that archive working for us. So we've seen in Greenland and in the Arctic profound changes. The sea ice retreat of last year was just huge and an enormous wake-up call to all of us. Do human beings cause climate change? I will say yes, and I won't say anything more because I don't need to say anything more. All right, I've answered your question, and I've not equivocated. I've not, given all the arm waving that I'm doing now. I'm just saying yes. All right. Now, as if you asked me that question as a scientist, are human beings causing climate change? I would go into all of the details and, how do we know that, and what are the uncertainties, and where are the areas, what's the soft underbelly of those uncertainties? Because that's what we do as scientists. We're always looking for the soft underbelly of our decisions. Where's the weak parts in that? I think if you do that with people, with the average person on the street, if you ask me, are human beings causing climate change? And I say, yes, but. As soon as I say but, I've lost the message that I want to convey. And the message I want to convey is that, yes, human beings are causing climate change. So we're in a situation where just from the raw number of people and the amount of resources we use, that we need more and more resources. We need more food, we need more water, we need more everything. What climate change is doing is compounding that problem. It's changing the baseline, if you will. If we need a certain amount of water in Africa or in Asia, and climate change reduces the total amount of water that's available, then that creates an additional problem on top of just the fact the population is increasing. Looking at these big problems that we face, in general, the problem of sustainability, how do we achieve sustainability, and all the subset underneath that of climate and water and food and all the resources, all the other issues. In looking at those big pictures, there are three actors that need to join together if we're really going to have solutions, effective solutions, and solutions that occur on a time scale that's useful. If solutions take hundreds of years, okay, that ain't going to work. And those three actors are the public, because they need to be educated and they need to put pressure on. They need to know it's their planet after all. It's our common backyard. The second actor is the information gatherers, the scientists, the policymakers, the people who gather the information that the politicians, the policymakers and the politicians and the governments use to act on. So I think if you don't have those three actors agreeing and working together, then things aren't working very well. If we're serious about stopping it, we're going to be doing some things that today's generation never even heard of these terms. You know, by the way, what is greenhouse gas geoengineering? Well, you know, we're all going to know that in 10 or 15 years. This will be on the cover of Time. Easy prediction.
Any questions?
As a climate scientist, I do my work in Greenland and Antarctica. That's where the big ice is.
That was one of the longer intros I've been subject to myself. Thank you all for coming. Thank you for inviting me to speak. It's not absolutely necessary because the organizing committee can outvote me, and they have done so on a number of occasions. What I'm going to talk about today leads a lot or follows a lot from Wayne's talk, and Wayne's talk was, I think, a very good introduction. I mean, you could tell from the question and answer that there's a lot of Q&A in this subject, so I'll try to leave some time there. But what I wanted to do is get a little sciencey on you and start out with some of the latest stuff we've seen in Greenland. And then that leads to some of the latest stuff, I'm echoing here, some of the latest stuff that we do and have seen about sea level projections, which feeds into a lot of discussion we had before. I've been working with a fellow who came up to me after I gave a public talk, and he works professionally in the area of risk and risk management. And not necessarily in the area of sea level rise, he just works in the area of how do you cost out risk? How do you plan for it? How do businesses deal with risk? And he was just fascinated by the idea that we really have not taken a lot of what we've learned in the business environment about how to deal with risk and translated that into environmental issues, oddly enough. So he was very interested in getting involved with me. He and I have been looking at a comparison of Miami and New York City, and since we have some interest in Miami here, I thought maybe we'd throw that in there. We can talk a little bit about that. Just in the last month or so, we released a new National Academy of Sciences report on abrupt climate change. I'll talk about that. I was the lead author on that. And that loops back to a little bit, if we have time, we'll talk about some of the latest findings from Greenland showing abrupt changes of very large magnitudes happening in time periods that are really quite difficult to understand, basically. So I'm going to start out with some results from the NEAM ice core. The NEAM ice core is just the name, the North Eemian ice core. We finished this ice core up in 2012. These results were published in Nature, I believe, or kind of in Science in 2013. And you'll see throughout my talk other names thrown up here because I do not pretend to be the sole source of any of this information. No. Really? Really? Greenland, so the new deep ice core is here in northern Greenland at NEAM. I'm pointing this out because a nearby ice core at North Grip I'll compare to. And we now have ice cores now from central Greenland. There's one in southern Greenland. Interestingly, we'd love to go back to southern Greenland, but as that really handsome guy in the intro said, it's getting hard. This area of Greenland now, that southern area melts more and more often in the summertime, and the planes that we take, the big C-130 Hercules with the skis on them, don't like wet snow any more than we like wet snow here, which we don't have to deal with in Breckenridge. But on the southern Greenland, we actually have to deal with. And that has made it problematic for us to go back to southern Greenland. But I'm just pointing out where these things are. So the big picture here, the Greenland ice sheet is about 3 million years old, which is an interesting number we can loop back to, because 3 million years ago was the last time that there was 400 parts per million CO2 in the atmosphere. It was a time called the Pliocene. We will loop back to that because that was a time when sea level was quite high, and part of the reason it was high is there was no Greenland ice sheet. Oldest ice found to date, however, dates just into the last interglacial, about 140,000 years ago, and you might ask what happened to all that other ice, and the answer is it all flowed into the ocean. So ice sheets accumulate ice, and then the ice sheds off into the ocean, so ice sheets are constantly ejecting ice into the ocean. There's all sorts of cool and interesting things you can think about. If you want a little on-air interesting thing. For example, this is a way in which viruses and bacteria, believe it or not, are reinoculated into the system and are preserved for 140,000 years in the north and about 1 million years in the south. And you can actually pull these bacteria and viruses out of the ice and regrow them. They revive even after hundreds of thousands of years. You'll note here, however, point I want to make is that abrupt change is really the hallmark of the this is where we are today up here. This is the glacial period, and you'll notice there's some large changes in there. And that was really one of the things we were after. But also the big thing we were after in this ice core, and I'm just keep walking here and drive Rob crazy, we wanted to extend, this is the North Grip, we wanted to get into the last interglacial period. Now, why are we interested in the last interglacial, or the name, the hunt for the last interglacial? This is a really dramatic movie, hasn't been made yet, but it will be at some point. I did want to point out that in 2012, when we were finishing up the NEEM ice core, something really remarkable happened. It rained, right? And we are here. And we are about as cold and as high as you can get in the northern hemisphere, and it rained. And we had a rainbow on the ice sheet. We don't get rainbows on the ice sheet. We don't even know what they look like. We can describe snow bows. We can describe snow dogs. We can describe all sorts of snow phenomenon for you, because we get those on a daily basis, but it just doesn't rain. And indeed, it rained on July 6th of 2012. That was a year, you might remember, 2012 was a year in which melting, this is the red map here shows melting, was extensive almost across the entire continent of Greenland. So why look at the last interglacial period? And the answer is pretty simple. It was warmer than today by a couple of degrees. If we want to look for an analog for the future, and I am a paleoclimatologist, I am actually Jay Prater's favorite paleoclimatologist. The closest analog, really, the closest analog in time that we have really is this last interglacial period. And that's 120,000 years ago. Believe it or not, we can actually get some pretty good records 120,000 years ago. As I pointed out before, if you want to ask a simple question, when was the last time we had 400 parts per million CO2? That's 3 to 5 million years ago. A lot harder to get good solid information about 3 to 5 million years ago. So this is a time period we're quite interested in going after. Sea level was higher by anywhere from 4 to 8 meters. So 6 here, the numbers bounce around a little bit. It was only slightly warmer than today, maybe a couple of degrees on average. It was a little bit warmer in the north. There was a smaller Greenland ice sheet in model world. So there's, I think we all talked about this, and you're quite familiar with this. There's always this loop back between observations and models, observations and models. You folks deal with that on a daily basis because your models are very highly dependent on observations, and your models are really only as good as what kind of observations kind of feed into those things. By the way, I think we all know this, observations are under threat from budget cuts as well, so we all need to be very, very careful about that. What we're trying to do here with this ice core study is provide observations, because right now really all we have for modeling the last interglacial period in Greenland, as far as what the ice sheet looked like, is models. So the models tell us that about 4 meters of that they think came from Greenland. So the lion's share, about 2/3 of it came from Greenland. So that's really what we were after here, is that indeed supported by the observations. Been a number of papers on this. COP in 2009 in Nature published a paper. And the sort of the number they give is about 7 meters higher than the present, and contributions of somewhere in a neighborhood of 2.5 to 3 meters each from both Greenland and Antarctica. The numbers don't really add up, but they never do. This is paleoclimate work. But basically about half of this from Greenland, half of it from Antarctica. So the observed records are here on the right-hand side. So this is the first part of the talk will be big science nerdy stuff, and then we'll move on to the less science nerdy stuff. This is the record, going from about 2,200 meters to about 2,500 meters. This period in here should have been the period of the Eemian. And you see, I mean, it's not as clean and crisp and lovely as we've seen in many other ice core records. There's a couple of things that I want to tell you about here that we do in the ice core community that allows us to intercompare ice cores and therefore tell whether or not we've got a record that makes sense versus a record that doesn't make sense. And that's, we know that the atmosphere is well mixed. So when we measure methane in Antarctica, it's got to be pretty close to the same methane record in Greenland. It doesn't have to be exactly the same because there's slight differences in the interhemispheric values of methane, but it's only slight. The O18, so we can measure the isotopes of oxygen. That one has to be the same because oxygen is very abundant in the atmosphere, and it's so abundant it doesn't change very much in terms of its either composition. It's very slightly decreasing over time, by the way, as we burn fossil fuels. The amount of oxygen decreases as the amount of CO2 increases. But we're in no danger of running out of oxygen. These have to match, and what we found in the initial look at the NEEM record was they didn't match. And the reason has to do with folding of ice at the bottom of the ice sheet. So this is kind of a cool thing here. When the NEEM project began, we had some fairly good radar records. So this is the same kind of radars you guys look in the atmosphere, we look into the ice sheet. We had pretty good records, but we didn't have great records. And over the time period of the life history of the NEEM ice core, there were significant advances in the radar that was looking down into the ice sheet. And so when we picked the NEEM site, we thought it was a pretty good site. And as it turns out, as the better radar accumulated over the 4 or 5 years of the project, it turns out we were not in the perfect place. I'm going to show you, so these are, you can see layers, radar echo layers. These are, because there's differences in density, differences in dust at times in the Earth's history. You can actually follow these layers. We can date these, we can track these layers all the way from Nîmes down to North Grip down to the center part of Greenland. So we can see these things in the ice sheet. As we go, so the map here on the right is taking you around the area of the NEEM ice core. But as we looked at better and better radar, you can start to see features at the bottom of the ice sheet where you see these ripples and waves. And these are ice flowing and ice waves breaking in the same way that atmospheric waves break, in the same way that ocean waves break, just a lot slower. Right? This is a really cool picture here, and this is now on the eastern side, or western side of the flow divide, down ice from Nîmes. And you can see these bumps. You can see what looks like the beginning of a wave beginning to crest in here. And because these layers of ice have different density, as ice flows, they actually shear and begin to break. It's the same physical principles that we have in the ocean that you have in the atmosphere. So the record I showed you looks like this as it turns. So this is the record the way as it should look. This is the record from Antarctica. And what we found was the only way we could make it work, sit and played with this for a while, wish we had algorithms to do this, played with it for a while, turned pieces upside down, rearranged things, and figured out, yeah, we've got the record, but 2 sections of it are completely turned over and actually repeated. Right? So putting it all back together was done by a combination of using the methane and the oxygen of the atmosphere and typically throwing in nitrogen-15 or something else, and putting together these 3-dimensional phase diagrams, taking ice cores from Antarctica where we know how these parameters vary over time and how they should vary, and then looking to see how the Greenland parameters vary and link in over time. And there's a couple of things that we notice on here right away. One is that things like methane and nitrous oxide have these big spikes in it. They shouldn't have those big spikes because they don't occur in Antarctica. And that's indicative of melting. So here we are. This is the warm Eemian part of the record. And what we're seeing is a lot more melting at that time than we see today, which is not surprising. Right? So it was warmer at that time. We're surprised at the amount of melting, at the degree of melting. And that'll be even more surprising, as I'll point out here in a second. So there's a number of things. This one happens to be O18 of air, methane, and the O18 of ice put together. You can see that everything really fits except for the crazy methane values. So this is how we put everything back together. If I can get the slide to advance. And I'll just skip in here. We don't need to mess with this. So what we think happened at the Nîmes site, it's a little movie here, shows that as the ice flows along, differences in density of ice at the bottom cause these waves, and differences in topography cause these waves of ice to form. They can come up, they can get top sheared off, and create a situation in which we have folding over. And then when we come along at some point and stick an ice core through this thing, we end up getting not only the record once, we get it twice. And then we'll get it once, and then we get it inverted. So the same sort of thing that you would see if you could sample the atmosphere in this way. You would see as those waves were breaking over the mountain, you could see that it was the same parcel of air looping around over and over again.
Hey, Jim.
Yeah. Matt Zafino.
Thank you, Dave. Matt Sapino, KGW. How do you know, so it sounds like you're using, if I'm hearing you correctly, Antarctica as kind of
Yeah.
a ground truth for this. How do you know that the Antarctic ice record didn't experience similar physical changes?
Excellent question. For a couple of reasons. One is that we can also compare to ocean sediment records the basic climate record that we see in the ice. Right? So we know it's got to look similar. So Southern Ocean records for climate ought to look like Southern Ice Core records for climate. All right, so if we see something really totally different, then we know we got either a big problem between the ice and the ocean or some problem with the ice. The other thing is that in Antarctica, because it's much lower accumulation, the areas we're looking at are way above the bedrock. So these are only about maybe 3/4 of the way through the ice sheet in Antarctica, whereas in Greenland, because it's a much more dynamic ice sheet and a younger ice sheet, we're looking at these features right down at the bottom of the ice sheet. Okay? So what we learned, all of this is leading up to this. What we learned from the NEEM ice core was a couple of things. One is that the temperature was as much as 8 degrees C warmer than today. And this is driven by a relatively small difference. I didn't show you the figure, but a relatively small difference in summer insolation. So there's a little bit more summer insolation 130,000 years ago, and that was enough to have a very different Eemian climate, as much as 8 degrees C warmer than today. This is backed up by a number of other records that we see in the Arctic, so this was not hugely surprising. The magnitude was a little more surprising. 8 was much larger, but larger than roughly the 6 or so that we were thinking it was probably going to be. We did see surface melting as evidenced by these methane values. By the way, I didn't point this out, but when ice melts and forms water, the gases, which will dissolve differently in water than they do in air, suddenly change their proportions. So for example, CO2 really likes to dissolve in water. And you will see very, very high levels of CO2 when you have a melt layer in an ice core. You can spot that right away. Methane will also go up, nitrous oxide will go up. And the ratio which they go up is the ratio of solubility of these gases in air versus water. So we can see that these things are indeed melt layers. Probably the most surprising thing was in looking at the total gas content in the ice. So the total gas content tells us roughly what the elevation of the ice sheet is. The higher up in the atmosphere you go, hopefully not news to you folks, you have less air. Yeah. So here we are at 10,000 feet, and we're all sucking wind, right? Well, we can measure the total gas content in ice cores and get an estimate of the elevation, or the elevation changes through time. And what we found at Greenland, or in the Eemian, was that Greenland seemingly did not contribute more than about 2 meters to the sea level rise. So whereas it was warm and there was a lot of melting, that part of the ice sheet had not lowered very much at all, by more than roughly 100 meters or something like that. So the northern part of the ice sheet really hadn't changed much, which constrains the rest of the ice sheet in terms of the modeling, in terms of how much ice could have been missing from Greenland at that time. Right? So many of my colleagues who are very Greenland-centric were not really happy with this message. I was pretty thrilled by it, because really what it does is it says we need to focus attention on Antarctica, because the sea level was indeed higher at that time by this 4 to 8 meters or so. And if Greenland only contributed a couple meters, that means Antarctica was doing most of the heavy lifting in terms of sea level rise. Now, that's important because Antarctica is a fundamentally different ice sheet than Greenland. And let me take a moment to talk about sea level rise and big ice sheets, because I'll loop back to that. But Greenland is mostly a land-based ice sheet. There's only a few spots on Greenland. We just wrote a proposal to go to one of the only ones where the ice is actually, its base is below sea level. And that might seem odd to you, but if you've got a lot of ice that's flowing off into the ocean, it can actually flow out there and displace the water and have the base of the ice sheet on sediments, but well below sea level. It can also happen that sea level was 100 meters, 130 meters lower in the past. The ice sheet grew and the sea level rose. Basically, now you've got a situation in which ice, its base is well below sea level. Greenland is mostly land-based, so there's only a few spots where Greenland has its ice below sea level. But the difference between an ice sheet where its base is below sea level and one that's on land, the difference between a marine-based ice sheet and a land-based ice sheet is fundamental in terms of how these ice sheets behave when it comes to a warming climate. If you've got a marine-based ice sheet, then you've got an inherently unstable situation because you have ice which wants to float in water which is not floating in water. Right? And so that is why attention focused to Antarctica becomes really interesting. Because the West Antarctic ice sheet, as I'll show you in a minute, is really a marine-based ice sheet. Now, I did want to stop here for a second because you get asked this question a lot. I'm going to show you sea level rise, and I'm going to show you sea level rise that's going to make you go, that's a total bunch of horse manure. But one of the most robust relationships in paleoclimate work on our planet is the relationship between sea level rise and temperature. When temperature goes up, sea level goes up. When temperature goes down, sea level goes down. And they are very much in lockstep. And the reason behind that is because the physics behind driving sea level up and down with temperature is simple. Right? So you've got a couple of things that happen here. One is simply as you warm the atmosphere, you warm the ocean. As you warm the ocean expands. So that's one of the reasons why sea level rises with warmer temperature. The other has to do with the impact of a warmer atmosphere and a warmer ocean on these big ice sheets. The warmer the atmosphere, you get melting. We all see that. What's even more important for an ice sheet, however, is you warm the ocean up, the ocean currents begin to erode the base of the ice sheet, and that causes an even faster removal of ice. Because as you all know, liquid water is going to have a much higher heat capacity, a much higher ability to take that cold away and melt that ice than air is going to have. So it turns out warm water is absolutely key to eroding ice sheets. Sea level and temperature. I mean, I can show you maps or figures of this, but this is basically, one of the, because that's such a robust relationship, as temperatures warm in the atmosphere, this is one of the reasons why we can say sea level is going to rise as time goes by. So if it's not Greenland, it's Antarctica. This is a map of bedrock for Antarctica, and you'll notice over here these colors. So anything in a bluish color is well below sea level, or sea level and below. And these dark blues that you start to get in here, these are, you can't read this, but that's 10,000 feet below sea level. So we are starting to get into a couple of miles below sea level. So basically, this doesn't want to be an ice sheet. This would rather, if given the druthers, this ice would rather shed off and go away. What's happening is the ice is coming out and finding somewhere out on these edges what's something called a grounding line. So the ice comes out and it finds a grounding. And when it finds that point where it can hit friction and stop, then the ice can back up and form behind there. All right? So that grounding line is absolutely critical to the health and stability of that ice sheet. Now what happens, yeah, Ned. Right in here. This is 0 right here. So anything green is above. All right, so the question was, where's 0? Anything green is land, above sea level, and anything in this lightest blue is right around sea level, and anything in the blues to purples is going to be well below sea level, current sea level. So what's absolutely critical here is this grounding line. So these ice sheets have come out, they've pinned. Did you want to ask a question? Okay. They've stopped. They've allowed ice to build back up behind them, and that grounding line is what keeps the whole situation stable. Now what's happening today is that warm water, typically in the relatively warm, you're talking about Antarctic currents here, relatively warm water, only a few degrees above 0 is going to be enough to carry away a huge amount of heat. Typically did not make it in, and underneath these ice tongues, the Roni-Filchner ice sheet, the Ross ice sheet, the Ross ice shelf, I should say, and I'll back up for a second. All along the coast of here, by the way, are areas where we see very rapid ice movement, lots of ice being shed into the ocean today And this is what's happening, is that now you're getting warmer currents which are being able to get in there and start to erode that grounding line. Now, back up for a second. I said Greenland's a land-based ice sheet. Land-based ice sheet, in order for it to shed ice into the ocean, basically it finds the low spots in topography. Like around the west coast of Greenland, there's one at Jakobshavn, a very famous glacier. But the ice is flowing in there. It's finding the low point between the mountains, and that's where it flows out. When you start to tick away at a grounding line, there isn't a low place, basically. These are sediments, marine sediments, and they're all pretty level. And so, whereas in Greenland, you may have only a few spots where ice can shed out, in West Antarctica, you've got pretty much all along the coast here. This is where you're losing it. This is when ice can start to flow out. So you have a much larger area that ice can flow into the ocean. Only really broken up by a couple of islands here, which actually probably help form the West Antarctic ice sheet. So the question for sea level and climate then is not whether if sea level will rise with a warmer climate, but how fast and how far. And this loops back around then to, I'll talk about this National Academy report. One of the areas, one of the places we pointed out as an area of interest for abrupt change in terms of sea level rise was West Antarctica. So we have very few observations of these warm currents. We have a few of them. We know these warm currents are beginning to happen. We know that ice is beginning to flow faster. But we don't put buoys out there. We don't put little gizmos out there to measure temperature. We measure the atmosphere, monitor the atmosphere far, far better than we do the ocean in general. And these very remote places around the world we don't go to very often, and we have very few observations. So really, what the report calls for is monitoring. And that's going to tell us how fast, and then really, ultimately, the other question is how far. And for us, it's really a question of how fast. How fast is sea level going to rise over the next 50 years, 100 years, 200 years, 300 years, et cetera. Sea level's rising today. You saw the figure from Wayne. It's about 3 feet, about a meter by the end of the century is the current estimate. And I'll point out, it won't stop there. And that's without West Antarctica. So the 3 meter that we now see in the latest IPCC report does not include a destabilizing West Antarctic ice sheet. So in order to get you a 3 feet of sea level rise, you have to have a certain rise rate over time. That rise rate over time is, like, as we're finding out with the IPCC, more than likely conservative. Matter of fact, the odds are very high that that's conservative. 3 feet is probably going to be on the lower end if that's the lesson. If indeed West Antarctica begins to contribute, sea level rise will be faster than that as time goes by. This is Miami with 3 feet of sea level rise, and there's some issues here. That's the airport. I'll talk more about this, but just to put the thought in your head, and I think I have mentioned this before in the past in this room. Really, the key here is not so much that there's salt water coming up here. It's power lines, it's gas lines, it's sewer lines. It's the infrastructure that you have to have in order to run a big city that's threatened by salt water. All right? So that's really when you talk about sea level rise, impacts on major urban areas, in the end, it's all about the infrastructure slowly getting attacked by salt water. John, do you want to ask a question?
Yeah, John Morales from NBC6 Miami. It might be worthwhile pointing out how Miami is not like the Netherlands.
Yeah.
I think many people think that the impact from sea level rise in Miami is going to be only at the coast, Miami Beach, as you see, Key Biscayne, the Port of Miami, et cetera, but well inland too. And the reason for the inland inundation is the porous limestone that is the bedrock
Yeah.
of the city of Miami. There is no way to hold back a rise in sea level by creating walls of any kind, because it's going to, or at least it's very difficult with today's geoscience to be able to do that.
No, and I'm glad you mentioned that, because that's exactly right. And this is one of the reasons why I use Miami as one of our examples, is because this is not defensible the way that Amsterdam in the Netherlands is defensible, the way that other East Coast cities are somewhat defensible. But this is definitely not defensible, because you build a dike around Miami and all you've done is basically created a bathtub, because water will come up underneath. You'd have to pave over the entire city. And I don't know how close you are to that today, but that takes a lot of effort.
Hey, Jim.
Yeah.
Howard Burns in WUSA. Cousin of mine, Steve Lazarus, is a professor of meteorology up in Melbourne and a former student of Howie's in front of me. And he was pointing out to me in Florida, John, you probably know this better than me, it's the aquifer there. Before inundation, the aquifer would be contaminated.
Yeah.
And the fresh water is more of an issue for there than the inundation.
No, that's right. I'll talk a little bit about that. We talk about Miami and New York City, the relative impacts. But freshwater along the Atlantic coast and Gulf Coast is already an issue. You talk to water managers for almost any city along the coast, particularly the Gulf Coast and the East Coast, and they will tell you that they're dealing with this already. They're having to go inland to find freshwater supplies because saltwater is already pushing. So the sea's already risen by roughly a foot in these areas over the last 100 years. Yeah.
Real quick, I just wanted to say, along what you're saying with these maps and stuff, quick shout out for Climate Central. We have a sea level rise program, and we've released a round of maps, and we're in the process of releasing a round 2 that incorporates all the 2010 census data. So it will show the impacts, how many roads underneath water,
Cool.
how many hospitals underneath, and it's in process of being released state by state. New Jersey, New York are out, and so is Florida.
All right, let me loop back to that. I want you to comment on that when I come back to that. Because one of the things we talked about in the National Academy report was we are way behind in terms of knowing what's at risk. We don't, we know there's trillions of dollars worth of assets along the coast. We just don't know, with a 6-inch or 1 foot or 2 foot exactly how much we have at risk here. This, by the way, is Miami with 2 meters of sea level rise, and this is, in the middle of next century sometime. What I tell folks is that, I think I talked about this before, Miami's roughly a city of 100 years in age right now. It's got another 100 years or so, which is, for 200 years is not a bad run for a city, but for those of you who live there now, this is not great news. I would point out that, when it comes to adaptation and resilience, something we're going to have to start thinking about is how do you get the hazardous stuff out of here? Because you don't want sea level to rise into an area where you've got, a nuclear power plant that you haven't gotten all the radioactive material out of, or you haven't gotten all of the oil and gas and all the other stuff that's located in tanks and stuff. There's going to be a huge cleanup job just to get stuff out of here. I also point out that this is going to be, if we do that, if we do the cleanup, this is going to be some of the best fishing in the world. Because we have created one of the most monstrous artificial reefs that has ever been. And as sea level goes up, fish are going to have a wonderful... You can't eat. It's not a... Okay. The problem there. So FAST is, and we'll come back to FAST here in a minute, so we have some idea of what we expect over the coming century. I'd say if we're missing things, we're missing some of the feedback, so it's going to make it go up even faster. Then the second question is, how far is this going to go? And that gets back to this question that I posed earlier. The last time we had about 400 parts per million CO2 in the atmosphere was about 3 to 5 million years ago, a period called the Pliocene. It was about 30 degrees Fahrenheit warmer in the Arctic. There were trees growing all the way up to the Arctic Circle. It's not clear that there was sea ice even in the wintertime. The models today get sea ice in the wintertime. We can talk about this. This is another study we put out this year, but it's not clear that you can even get it 30 degrees warmer. Well, let me put it like this. When we take our climate models that we have today, our GCMs, and we apply them to 3 to 5 million years ago, we can't make it warm enough. So we're missing some feedbacks in that system. There's certainly less sea ice, less land ice, and sea level was about 20 to 25 meters higher than today. We've talked about this in this room. This gets back to my point made earlier that when you look at really big time and you look at large changes in sea level that are associated with small changes in temperature, you see a very good relationship. It's not necessarily linear, but you can throw points on here and you can see some variability. But in general, this is a pretty relatively linear relationship. I want to point out that the scale here for temperature is actually not that big. Here we are today at an average global temperature of 15. During glacial times, it was about 5 degrees colder, and it was about 130 meters, so 400 feet or so lower sea level at that time. This is the IPCC forecast for the year 2100 in terms of temperature. that would map onto a sea level of somewhere around 40 meters, if indeed sea level followed temperature slavishly. Now, it doesn't follow temperature slavishly, and it's because it takes time for ice to melt. It takes time for these systems to shed ice into the ocean. And that's why I keep saying it's really a question of how fast these things are going to happen. Now, note you go back about 40 million years ago, that's about when Antarctica formed as an ice sheet. And there we don't expect this curve to keep going up. It'll go along a line of thermal expansion of water at that point. All right, so sea level doesn't just keep rising. Brad. Can I
Brad
get some water?
Panovich, NBC Charlotte.
Yeah.
Jim, I'm curious, the time scale is different. How do plate tectonics play into this? I mean, does it exaggerate? Does it counterbalance some of this?
The question is plate tectonics, and yeah, there's, I don't have time to go into it, but for any given location along the coast, you have to take into account a bunch of factors to determine what sea level rise is going to be. It's going to be a question of ocean currents, local ocean temperature. For example, sea level is rising faster in the Arctic than it is in the tropics because the ocean in the Arctic is warming faster. So it'll vary, and it also varies by tectonics. So, at this time there were huge ice sheets. Those ice sheets smashed down the crust, and there are places in Canada and in Alaska where it's still rebounding. So these are areas where you may never see sea level, not never. At 40 meters or so, you're going to see it. But, for a long period of time, you won't see that kind of effect.
Jim, it's probably worth mentioning STEM. You got Louisiana.
Thank you for that. There are areas that are naturally sinking. This area, for example, is naturally sinking. Yeah, we're not. There's a whole lot of things. Actually, I have a good friend of mine at LSU we can bring here to talk about. If you're interested in that, there's all sorts of interesting physics that go on in the delta region that determine subsidence levels. This, by the way, is 20 meters of sea level rise along the Gulf Coast in Florida. We'll come back to this, but at this point, Miami's don't worry about it. I've pointed out, I think we've done this in the past. When I give public lectures on this, I try to give people a sense that, life isn't going to end. Life does go on, and we can have some fun with this. And so I'll ask you folks, what's the most important thing in this part of Florida? Disney World, yeah. We've talked about this. And the beauty is that either through the Jacksonville River drainage or up through the south, you can sail the Disney Princess and the other big, right up to the Magic Kingdom. So this is, there is some good news in here. There's some interesting news in here. This is 20 meters. So one thing we don't think about is one of the areas that we use for growing a lot of our crops is well below sea level, the Grand Valley of California. And right here is a passageway. It's called the Carquinez Passage. But, we'll build a dam there. I mean, why not? There are many people who don't like Sacramento for many reasons, but, there's no reason not to build a dam right there. And then I've used this example for you. This is one of my favorite examples of sea level rise. And so 20 meters of sea level rise. What state is this, class? Delaware. Okay. So, what was the first state of the Union? Delaware. Delaware was the first one to sign on. They're very, very proud of that, right? So all you need to know to remember sea level rise is first in, first out. All right? That's all so FIFO. And,
Delaware Keys.
yeah, and it's remarkable. Years later, I will have people come up to me, like in a restaurant, and they'll just point at me and go, FIFO, dude. And it's like, okay, you got it. They remembered that there are major impacts. Howie.
When climate scientists try to assess the possible change in frequency of occurrence of tropical cyclones, do they take the change in sea level into account like this? For example, if South Florida goes, you've got more ocean.
Right.
Storms may intensify more before they hit land, that sort of thing.
I don't know that that's been fully explored. So this is a very good, basically what you got here is a whole shelf area of very hot water that doesn't have cold water underneath it. So in terms of hurricane impacts, there are some things that have to be built into models, and hurricanes may behave differently under these scenarios. Actually, hurricane reconstructions are something we would like to get better at, but it's really hard to do hurricane reconstructions that far back in time. I used to stop there. I won't stop there these days. If you fully melt Antarctica, which is what you would get if, we're at 400 today, and we haven't done a thing about limiting greenhouse gas emissions. So we'll make it to 600. That's my easy guess. Will we make it to 800? Will we hit the big 1000? I don't know. But, when you get up to around 600, 700, 800 parts per million CO2, you got to go back 40 million, 50 million years in the past, right? That's, when dinosaurs roamed the earth and Raquel Welch wore, furs and, way, way, way back in time. That's, there you're talking about, sea level of, even higher than that. So 60 meters of sea level rise. And so this is just a map of what the eastern part of the United States looks like if you were to melt both of those ice sheets. And, for the geomorph geeks in the crowd, and I know there's none, you can actually drive along. For example, you can drive down here, any of these interstates coming down through here to the beach. You can see these old beach lines. You'll be cruising along and the road will drop. And you'll go, I wonder what that was. Well, that was an old beach line. That beach line happened to be 40 million years. But if you take away the ice, you have if tectonics doesn't change the land very much, and these have been pretty stable areas, you get a very well built-in beach line because it's stable for a long, long period of time. So you can actually still see these. Okay, so now I want to very quickly go through, and I hate it when I do that, talk about what Rob Mott and I have been doing in looking at Miami and New York City and their responses to the threat of sea level rise. We are no social scientists, so I don't claim we know a whole heck of a lot. I will say that we have been in contact with Ed Maybach and his crew to talk about ways in which we can do this better. And they're actually interesting. I asked Ed, because Ed's spoken at this conference, I said, have you done much in the way of sea level rise and public response? And very little has been done. There's some in Florida. We'll talk about 7 counties. And there's been a little bit in Maryland. But it's not a very often asked question. How do you feel about sea level rise? So I sent Rob down to Florida. He went to a sea level rise conference down there. I believe it was in Tampa. So a little bit of background. So for those of you who aren't familiar, there's a conglomeration of counties that have come together and put together a regional climate action plan, which was published in late December and in late 2011. They are looking at somewhere in the neighborhood of 1 foot to 2 feet of sea level rise by 2060. Interestingly, 2100 is a number that is burned into my brain as a climate scientist because we used to use that as, what's climate going to be like in 2100? It's a nice little... as we build more social science into this, we're realizing that 2100 is way too far out in the future. So let's start talking about 2040. Let's start talking about 2060. Even 2060 can be a problem, but let's start talking about time. And so when they put together their report, 2060s was their target plan. Some observations that Rob had from the conference and in talking with folks down there. In general, they believe in the projections with some caveats. If you haven't read the Rolling Stone article on sea level rise and southern Florida, read it. It's really interesting. They did a very, very good job. There was significant talk at the conference about managed retreat. How do we manage moving the cities back from the coastlines? That's pretty dramatic talk if you think about it. There was a guy there, Sam Poole, who was the former executive director of the South Florida Water Management District, basically said, I'm going to sell my house within 10 years and rent it out, because he didn't want to be stuck with the house. There were lots of jokes about North Carolina. So this is an interesting sociological phenomenon that, and southern Florida is not doing that much about sea level rise, as you'll see, but they will point the finger at other people who are doing even less. And, our good friends in North Carolina were able to, provide Florida with that lower rung on the ladder. Levees, and John just pointed out, levees were not discussed as a protection option. Although, interestingly, you folks down in southern Florida have hired Dutch consultants to come in. And they probably told you we can't do a thing for you. And by the way, our fee is $200,000. So what actions are they taking? They're incorporating 2030 and 2060 sea level rise projections into their work plans. There's a lot of saltwater intrusion modeling that was asked about earlier. Health effects are being tracked that go along with that. There wasn't much in the way of future scenarios in terms of, southern Florida's gone. So that kind of, while there's some acceptance of sea level rise, there's not full acceptance of the extent of sea level rise that we expect to eventually happen. Some say Florida has done less than other states in dealing with sea level rise. For example, they're still building on the beach. These counties down there project a 50% population growth between now and 2060, the same time period over which they expect to see a 2-foot rise in sea level. So pretty much all, policy actions, you're seeing sometimes a really big mismatch between one side saying, well, this is what's going to happen here, and maybe, the Chamber of Commerce saying, hell with that, we need 50% population increase in order to keep the economy percolating along. So it's not surprising, but it indeed, this kind of mismatch between one side and the other does go on. Yeah?
Jim, could you touch a little bit, because what you're talking about is very important, but I think that there's a big gold star here because at least they're doing something.
Yeah.
So can you talk a little bit about how you think they've come over the past couple of years closer to taking action?
Let me put it this way. In southern Florida, at least the conversation's now starting to happen. I'll compare that to New York City, where there's been a lot more action. But southern Florida needs to go a long way. Southern Florida is at the bullseye of sea level rise when it comes to North America. And they're way behind the curve in terms of accepting this. And I'll give you some examples of that here in a minute, Sarah. So there's a bunch of issues. As a matter of fact, it's on this slide. Communication with the public is a big issue, probably the biggest issue they have. The folks who were at this conference pointed out that the public was skeptical and downright hostile. So going into an area and talking to them about sea level rise, you would just get clobbered, right? So they didn't want to hear about it. Even though this is a physical reality and you really cannot rearrange the physics of our planet any more than you can, pass a law that says gravity isn't going to work today, you've got people who don't want it to happen, and they don't want to talk about it. They talked about the fact the public will tune out if you talk 2060 and beyond, so take a step at a time. Keep the scientific message simple. Don't go into reason. I love this line. Concentrate on financial impact. So don't go into reasons why these things happen. Just tell them this is going to cost you money, which is why we talked about this the other day. I was saying, that if indeed I have to pay for somebody's insurance who lives on the coast, that pisses me off and I don't want to do it. All right, so that's one of the things you can talk about. Modern governments, so this is something that's changed a little bit in our society. Modern governments definitely need community involvement and okay in order to move ahead. And this loops back to here. So when you've got a skeptical and hostile public, it's hard to get politicians to deal with it because they're going to get voted out of office if they deal with this particular subject. Netherlands, Rob's been comparing Miami and Netherlands also. Netherlands, very, very different situation. People there understand sea level issues, they get behind the government, and so action becomes much easier and happens much faster. So unless you have the public behind it. So this is one of the reasons why I wanted to talk to you folks about this, because unless people sort of get told this over and over again, they're not really going to accept that this is going to happen to them, and is happening to them. So what's stopping bolder action? Back to your question, Sarah. I don't know. I misspelled it, too. I've debated over whether the word ignorant should be in there, uninformed. Face it, they're ignorant. They don't know that this is happening. They don't understand the reality of it, the physics of it, that you simply cannot get out of it. So as I just pointed out, as most government processes now involve public input, this makes it very difficult. There's a whole bunch of mixed messages from elected leaders. So for example, there are a number of state employees of Florida who gave talks, and once one person slipped up and used the word climate change. They're not allowed to say that at a meeting. All right? But the governor says, no, you shall not use, if you're a state employee and I write your check, you can't use the word climate change. So there's a similar message from a Virginian who was there. The phenomenon whose name must not be said, right? Was how they were referring to it. So, there's some active pushback against this, and I think we all understand it. So certainly, definitely a lack of belief in climate change. You have to avoid the discussion of climate change. You avoid the issue of why sea level is rising and focus on the impacts. You just say it's rising, get over it. They were forced to talk about surge protection instead of sea level rise. So surge protection also goes along with it. As we all know, as sea level rise goes up, the surge goes farther inland. So if you just talk about surge and you bury the sea level rise down there somewhere, you can get away with that. A lot of people don't believe in the science. Interestingly, this is from a 2009 study. Less than half of the politicians, the decision makers, in the Keys didn't believe that sea level rise was likely going to cause them severe problems. The Keys are toast, folks. I can't say it any more bluntly than that. It's also an issue of a faraway problem. So when we talk about 2060, people just immediately tune out. It's that, we can grow the population by 50% while at the same time sea level rises by 2 feet. No, you can't, but, both plans are steaming full speed ahead. It's a very big issue to wrap your head around. For planners, it's really an overwhelming problem. The idea that you have to abandon at some point, have to have phased retreat, this is really, really very challenging for them. There's an inherent belief by people that a solution will be found, that this won't happen, right? that we'll stop this. It's really hard, they found in talking with people, for people to deal with a moving target. So sea level rise is one of these creeping things that happens, rather than just suddenly wham in your face, like an abrupt climate change. So it's hard to get people to deal with that. It's a very difficult message. How do I tell the person that their house may wash away and we will stop them from rebuilding? There was talk about retreat, but there's also, how do we avoid the Detroit syndrome? We don't want to be Detroit. Can't just hand over the buildings to the government. We need to use managed location terms, not retreat terms. There was a lot of bravado talk, which we also have heard in New York City. We do not retreat. We will hold strong. We will get our feet wet. Yeah. Yeah. I'm going to speed this up here because sadly, I'm not going to make it through my talk, as usual. Insurance, and there's, I put this in red here because a lot of people believe this may be the first shoe to drop, that when you can no longer get insurance. When the insurance companies pull out, that's going to be the first real wake-up call to people that, hey, we're not going to be able to handle this. Today, the average subsidy for a coastal mortgage is about $2,400 a year in southern Florida, about $72,000 over the lifetime of the mortgage, going from your pocket to somebody else's pocket if their house is right on the beach. And there was consensus that the big winners in sea level rise are going to be, wait for it, the lawyers, right? There's a whole bunch of legal issues that are already happening and will continue to happen. Suits against realtors. You sold me a house. Now they tell me that my 30-year mortgage, by the end of it, my house is not going to be worth anything. I'm going to sue you, all right? Homeowners Association rules that restrict mitigation efforts. The homeowners associations are getting sued. Regulations and codes to force relocation. Environmental damage from flooded buildings. So if your next door neighbor's got some toxic stuff coming out of their basement, this is a problem, you sue them. Mortgage companies are getting sued. There's a whole bunch of unfunded mandates that are happening where towns are having to take refugees. As some areas become uninhabitable, they got to worry about taking them. And then malpractice. There's a whole bunch of stuff. There was a bunch of people who projected that environmental court would become a term within the next 15 years that you'll hear more and more about, that as some of these issues come to fruition. I'm not going to go through this. There's health effects as well. I would point out that we're spending about $1.1 billion over the lifetime of the project to rehabilitate the Everglades. 60% of the Everglades is below 3 feet of sea level, so this is federal dollars. We're all paying for this. Really some question about just how smart that is. And interestingly, publicly traded companies. So the Securities and Exchange Commission requires public companies to disclose the risk of climate change. Only 25 companies reported risk due to sea level rise, mostly energy companies. And that's numbers way, way, way low. So there's a lot of either denial or misunderstanding of the scope of the problem that's going along with this. Okay, very briefly, I want to go through New York City. Whereas Miami had a couple studies, New York City's got like 10 of these things. So there's all sorts of studies in New York City. They are looking at about, actually less sea level rise than they were looking at in Miami, but still a sea level rise. The report does not go beyond 2050. Again, bravado, we cannot, will not abandon our waterfront. But in New York City, they throw money at this, right? So there was about $19.5 billion, we hear the number $20 billion thrown at dealing with the city after Superstorm Sandy in about a 10-year time horizon. By the way, this $20 billion excludes the MTA, the subway, because that's handled by the state. So these are city impacts and city studies and city dollars. So there's a whole raft of state dollars that aren't even counted here.
Does it include closing down the George Washington Bridge?
Yeah, that's New Jersey. So there's a couple of important things here. They debunked sort of a silver bullet harbor-wide plan. Originally talk was we'll just protect the whole thing, and they went, okay, we got to be smarter than that. We can't do that. It's based on Swiss reinsurance study of and modeling of damages. Let me just get through this pretty quickly here. So they input data on sea level rise, frequency of storms. So this gets back to your point, Howie. City provided asset data along the coast, mostly by Swiss Re. And then they output, so the way that they do this is risk management tools they use. They calculate what's the annual exposure to risk. Now, we all know it doesn't happen annually, but what's my annual risk here on a year-by-year basis, knowing that that's going to accumulate and I'll have to pay it all off. But the insurance companies have to accumulate the dollars over time so that they can pay $60 billion when they need $60 billion. So the losses are running about somewhere between $2 and $4.4 billion annually. That's what the reinsurance companies think the city is going to have to collect, or the insurance companies are going to have to collect in order to insure the city. This goes up with time. $19 billion in 2012. In 2050 dollars will be about $90 billion. So the amount of money that has to be accumulated over time is pretty impressive. And this is just to protect New York City. So there's a whole bunch of strategies they're using. I'm going to skip through this. Interestingly, about almost all the buildings in the area were constructed before 1983, when there was some new regulations went into effect, the base flood elevation regulations. Simple stuff like you cannot have your oil tank in the basement because if you're in the flood zone. And this we saw a lot. We saw people who had the basic home and building infrastructure was in the basement. And so when the water came in, immediately your heating got cut off. Immediately you had, heating oil leaking out into the system. And so there's a whole bunch of regulations that now say you can't do that anymore. Interestingly, about half of the city generating capacity is now in the floodplain, and it's expected to rise to about 97% by 2050. So that has to be dealt with in New York City. In terms of transportation, Sandy caused about $8 billion in damage. So there's a whole bunch of work that has to be done hardening tunnels. So I don't know if you remember, but there's a bunch of tunnels that go underneath the Hudson, and they were compromised as well. Ferry terminals, traffic light controllers, so basic stuff that you don't think about until you get a storm surge that fries all of the electronics in your traffic light controllers. And again, this doesn't include subway actions. So New York City is actually doing something. They're trying to do something. I think they recognize that they've got a problem that is also going to involve managed retreat as time goes by. They also, even though they are well aware of the long-term impacts, the 10, 20 meters kind of thing, they don't plan for that either, because they don't, again, I don't know if they know how to plan for it. I love this diagram. This came out of one of their reports. This is the threshold height of the New York City subway system. And over from the 1950 to 2000 time frame, there were many, many storms that came along with storm surges that got close but didn't do it. And this is a classic example of a threshold in our systems that gets pushed over the edge by a change, a small but gradual change in the environmental system. And this I'm going to talk more about here in about 10 minutes. We talk about the report that we put out. We talked about the fact that abrupt change is not just abrupt changes in the climate system, but even if you had, say, a slowly rising sea level, if that then reached the point where the probability of a storm surge overtopped your subway threshold, that's an abrupt change. And that was indeed an abrupt change when it came to Sandy. Because something that was multiple billion-dollar problem became a much, much bigger problem when the subway system flooded. It was a huge cost to deal with that. Okay, so that leads me to the report. So what we did in this report, as I said, there's a couple of differences in looking at abrupt change. We not only looked at abrupt changes within the climate system, but we looked at how human-built infrastructure and also how ecosystems have thresholds. So a slowly changing temperature can push a species out of its existence zone and make it extinct. So that is an abrupt response to a slowly changing system. So this is something you'll hear more of as time goes by, that our definition of what's abrupt has changed. You've all seen this, so we won't skip over it. So the new report was that we were also asked to think about the idea of an abrupt change early warning system, and I'll come back to that in a moment. I would say that so we've known about these abrupt changes since the late 80s, early 90s, when the first papers were published on this subject. The first Academy report was in 2002, about a decade after that. And so this report was about a decade after this. The Academy is probably going to keep looking at this as time goes by. What are these things? They're large and rapid changes. I think probably this is important, faster than expectations. I'll take something from a slide that's coming up because I know I'm going to run out of time. So what do I mean by faster than expectations? I got a phone call from someone who works in the air conditioning industry. And he builds very large air conditioning systems for companies like Google and Microsoft. Companies have these very large server farms and need very large air conditioning systems. We're talking 10, 20, 50, $100 million air conditioning systems. And interesting question, he says, what's going to be the maximum high temperature in this certain area in 39 years? And I sort of paused for a moment and said, well, why do you want to know? And he said, well, I work in the air conditioning industry. He went and told me. 39 years is the time period over which the federal government allows you to write off air conditioning systems if you're a big business. And so what they wanted to know was, so this has been happening, that a company will build a server farm with an air conditioning system, and then that system won't last more than about 15 years because the average high temperatures have been getting higher and higher and higher. And these systems are so expensive that if they can't write them off over the full 39 years, it's a financial loss to the company. So they want to know what the target's going to be out here. So this is an example of something that's changing faster than expectation. It may not seem abrupt to us, 39 years, but it's abrupt when it comes to the dollars that are involved here. Right? Yeah.
What did you tell him?
Oh, actually, wait, yeah, we took some climate model projections and said this is what we think is going to happen, and it's better than, actually, pretty much a linear extrapolation of what we had. Really can't do a whole lot better. So we talked about this, some examples of abrupt changes that are already happening. Wayne talked about decreasing Arctic sea ice. There's increasing extinctions. Areas that need more research, already talked about this, the Western Arctic ice sheet. Interestingly, science is always constantly looking at these issues and then reevaluating what's a threat and what's not a threat. If I had talked to you 5 years ago, we would have talked a lot about meridional ocean circulation, the North Atlantic deep water, and how if that shut down rapidly, that could cause an abrupt change. The models now today agree quite well that the odds of that happening in the coming century are very, very low. That this is a system that will not just collapse on us in the coming century. So what used to be an abrupt threat is now been pushed down the radar a little bit because we studied it, because we understand more. Another interesting one, and I get asked this a lot, is, so we talk about this in this room, there's as much carbon in permafrost as there is in all coal, oil, and natural gas, and that stuff's melting, and that carbon will come out into the atmosphere. And there's been a lot of interest as to whether or not that will happen abruptly. Will you see a very rapid increase in CO2 and a rapid increase in methane as these permafrost soils melt? And as we've studied them, particularly over the last 4 or 5 years, we've come to recognize that there are thermodynamic constraints on how rapidly you can make this stuff go away. So whereas methane and CO2 is going to increase from melting of permafrost, that's going to happen. It's not going to happen abruptly. And so there's some good messages lurking in here inside the bad as well. So some key points I already talked about, air conditioning systems. We got asked this question a lot. What does this cost? What does it cost to take together the observing systems that they have at NOAA and NASA and other places, put all this stuff together? And actually, it's ridiculously small relative to the value of what's at stake. And I'll give you a couple of scaling factors here. Ecosystem services are like fresh water, clean air, pollination, all sorts of stuff that nature does for us that we don't think about. Many, many studies have been done over the last 20 years. That's worth at least the global GDP, if not 2 to 3 times the global GDP every year. So we're talking trillions of dollars a year, annually, at stake if we don't pay attention to the environmental changes that are happening. We already talked about this. There are trillions of dollars. So roughly 40% of America's assets are located on the coast. 40% of our economic muscle is on the coast, right? And we don't know. That's again, trillions of dollars, which is way less than what they give Wayne, all right? Way less, right? I can tell you that. Way less. The example I give for when people ask about it is, think about banks. You walk into a bank, all right? There's sophisticated security systems. There are cameras. There are security systems you don't even see that are lurking in there. And those things have got to cost hundreds of thousands of dollars, if not more than that. Yet the bank is willing to pay that. Why? Because the value of what they've got stored there is greater, far greater than the value of that monitoring system. It's the same reason behind, you hate them and I hate them. Those cameras they put up to catch you going through stop signs or speed, those things cost money. And we as the taxpayer pay for those things. But they pay back because they catch us speeding more and more and more, right? So basically, the idea that a system like this may cost, hundreds of millions of dollars is kind of, that's not the point. What's at stake is trillions and trillions of dollars. And are you willing to go blindly into the future, or do you want to go into the future with some idea of what's at stake and some idea of how to triage? Where is it that I want to focus my efforts here? Is it the sea level rise issue? Is it groundwater? Are there other things I want to focus on? I do want to talk very briefly, and then I'm going to quit and we can do questions. This is the gravity satellite system that we put up about 10 years ago in the early 2000s. I mentioned this in a talk a couple years ago, just very briefly though. So these satellites were put up there to measure small changes in gravity at the Earth's surface. So, the gravitational attraction is a function of how much mass is below you and how much mass you have. Turns out that the amount of mass below your feet is a function in continental areas of how much water's in the ground. That's the number one reason why gravity changes over time. And so what they did, I don't know if they did this on purpose, but probably not. They ended up measuring groundwater acquisitions or removals over time. And so there's a 10-year record of this. Now, you can't get down to detail because we didn't spend enough on the satellites to do that. But you can see on here, red colors, anything in the yellows and reds is removal over that time period. And you can see in here, all this yellow in here, the high plains groundwater depletion that we know about because we have monitored this. We ran into problems with the Ogallala with the High Plains Aquifer back in the 50s and 60s. We began to monitor it better. But look at this. You've got areas of the U.S. where we do not focus on groundwater at all that are seeing large decreases in groundwater. The Southeast is a bullet point for the U.S. Now, it rains there, right? What's the average rainfall in Atlanta, Jim? 50 inches. All right, you would think that 40, 50 inches would be enough. But as it turns out, if you're a farmer and you don't get rain when you need it, and your crops at risk, you really only have three choices. You can either don't grow the crop and let somebody in Chile do it, which is not a very attractive option if you're a farmer. You take out of storage what you saved from last year, which doesn't happen anymore. For those of us who grew up eating government cheese, you know that used to happen. Or the third thing you do is you draw water out of the ground and you grow your crop anyway. So groundwater is the insurance policy that farmers have to deal with drought. And what's been happening in the Southeast is it's been withdrawn faster than it's being put back in. And we all know that that's a system that fails at some point. Unless rainfall rates go up dramatically higher and recharge this, then you're going to have a problem. You're going to reach a point where the farmers in the Southeast aren't going to have the groundwater there to ride them through droughts. This is that's 10 years of everything. So this is a satellite looking down 10 years of everything. All right. So there's a couple of points in here. One is that we didn't anticipate that this would be a problem area. But the other is we don't monitor groundwater as well as we should. So again, you know, there are cameras located on the street corners. There are cameras located in banks. We monitor ourselves all the time. But when it comes to looking at nature, we don't do it as much as we should. And yet there's even more at stake in the Southeast in terms of groundwater shortage than there is for all those cameras on the streets. Yeah, Sarah.
Sarah Maxwell, Storm Center. Is this have anything to do with increasing population and increasing draw upon the water in that area, or is this strictly an environmental impact that you're talking about?
Like you know, we've heard over the last week, like most of the things we've heard over the last week, it's a combination of an increased demand from an increasing population, an increasing water usage, on top of probably a changing baseline in terms of climate, in terms of more extremes. We've seen this as well.
So as far as adaptation goes, wouldn't a lot of these farmers just move northwestward? I mean, is that an answer?
Well, last I heard, there were people in Ohio. Is that true? I mean, I don't know. Yeah, I mean, I say that facetiously, but you know, where are they going to go? What are they going to grow? So you know, just knowing that you've got an impending drought problem is knowledge, and knowledge is good. All right, and that's really what's lacking here, is we don't monitor the systems well enough to know this is a threshold, this is a tipping point. Where's the problem going to be? Because if we communicate to farmers, hey, you know, we've got a problem here. We did that in the High Plains Aquifer, and there are laws and rules and regulations about withdrawing too much groundwater. The same kind of approach could be taken there. Farmers didn't like it there, they won't like it here, but it means you have sustainability, it means you have some resilience. Matt.
But I think to follow up on Tori's microphone, right? Hello, microphone. That's, you know, follow up on Jim's point about this being a short record. I'm assuming what Jim meant was that it was only a 10-year sample, and if we looked at a 100-year or a 50-year sample of the groundwater in the Southeast, would we see a natural variation that I would assume would correspond with but lag rainfall or drought? Yeah. So I guess the question is, can this naturally recover and respond on its own if they, you know, I think Dale just said they've had 80 inches this last year.
Yes, it could. What I'm pitching here is knowledge. Monitor it. Know about it. Do better than we've done in terms of actually watching. Because we don't even think about these things as a problem. If you've got 50 inches of rain, you don't think, hey, we could have a drought. But you guys have been through droughts in the last 10 years. Right? And it's not an insignificant problem. And again, you know, what used to be a drought, you know, what had to be, you know, way low, like 20 inches of rain. But with more and more demand on the system, Matt, it's now 40 inches may be a drought. Because drought is, I think I've said this before, drought is no longer a meteorological term Drought's an anthropological term, because it's how much water do we need to do what we need to do.
Yeah, Jim, I was going to say, Brad Panovich, NBC Charlotte. I mean, there's a lot of research in the Carolinas about cyclical droughts, and they go back pretty long period because of the position of Bermuda High, parking over the southeast. And we've had years where we get 20 inches water restrictions. A year later, we get 70 inches, and the policy makers forget about all the things they wanted to do when we only have 20 inches. But I think Sarah's right as well. The population growth, Duke Power is dammed up the Catawba River. If we didn't have some of these lakes, the water system would be strained even more in these drought-stricken areas. So we are drawing a lot more water than we used to, and we know that these cyclical droughts are going to happen. They may get longer, and this year is a bad example because we have Western North Carolina, 100-inch, rainfall amounts this year compared to 2 to 4 years ago when it was like 30, 40 inches.
It's interesting because that kind of thinking has been going on in the West for a long time because we're so short on water. But the same kind of thinking, how many reservoirs do I need and how big do I have to build them? The engineers will tell you need at least 5 years of water backed up. Well, 5 years of water at what rainfall rate? And that's where it starts to get more interesting. And again, my pitch here and the pitch in the report is know what the problems are, and monitor the problems. Because going into it blind is not a good way to go through, fat, drunk, and stupid is not a good way to go through life. With all apologies to Ken Earhart. I'm just going to take questions. I've given up trying to show any more slides. So we've only got about 8 minutes, 10 minutes. So any more questions? Yeah, Howie. Or any more discussion?
I'd like to ask a totally different type of question. When you talk about abrupt climate change, could you include chaotic effects? I'll never forget a talk that Ed Lorenz gave at the eponymous Ed Lorenz Symposium.
Yeah.
And he had a simple, it was a 3 or 4 variable nonlinear model. And you run it along and he looks at a variable, say, like temperature, and it goes along pretty steady. And all of a sudden, it changes abruptly, jumps to another level, stays at that level for 5,000 years, and then comes back and so on. That, to me, looked like an analog to abrupt climate change. Would you care to comment on that?
Yeah, so the triggers to these things are they chaotic? Are there actual points in the system? For example, a lot of those changes in Greenland, we are beginning to understand can be attributed to because you had an ice sheet, which we don't have today, the jet stream had both a northerly limb that went over the pole and a southerly limb that went around the bottom of the ice sheet. And that northerly side was very important in keeping that area ridiculously cold up in Greenland. As soon as that northerly limb collapsed, and the reason why it collapsed is the subject of research, then suddenly Greenland can warm up. And I don't have time to show you, but we've seen changes of 10 degrees C in mean annual temperature in Greenland in 1 or 2 years. 1 or 2 years. So that's clearly, got to be atmospheric. It isn't oceanic. But yeah, are these causes? There's a whole literature now on the causes. Are they chaotic? Are they? Is there some other physical system that's pushing the system? There's a whole bunch of research that's being done on that. Yeah, Howie.
Earlier, when Wayne was talking, we talked about going back beyond with some of over the ocean with the temperatures, and you were going to elaborate on that, just how you know or how you make the best guess of what the temperature record over the ocean surfaces was going back before we had the satellite era.
Yeah, so there's a couple of realities. One is that we know we're going to have far less coverage of the ocean when you go back past roughly World War II. So World War II was a threshold as you know, in the Earth monitoring business, in the weather business. We suddenly had a really good reason to know what the weather was going to be in 3 days. We had a good reason to know what was at the bottom of the ocean and how temperatures changed in the ocean because we had to find submarines, things like that. So any data before about 1950 is sparser. The way that we have temperatures from them at all is ships used to take ocean surface temperatures as they went along. They would lower a bucket over the side, they would bring the water up, and they would take the thermometer.
Resolution had to be.
Yes, it is not good. But there's enough observation, so there's enough ships around between 1900 and 1950 or so that the error bars are larger, but we know that the temperature was, statistically different or not statistically different, just based on the, because if you only monitor 10%, you have to have a much larger error bar than if. Plus, there has to be all sorts of corrections for bucket temperatures to actual surface temperatures. There's a whole bunch of science that's gone into that. But I think probably the best thing I can tell you is take the temperatures between 1900 and 1940 in the ocean with a grain of salt, water.
But see, they can actually. You can download the data from the National Climatic Data Center. You can see what those errors are.
Yep.
And it's through spatial regression that the points are extrapolated out over the ocean. So it's a good point, but it's
Just wanted an
transparent.
understanding on the process, that's all.
It's basically taking sparse observations and trying to infill them, trying to understand what the errors are. Some people took better measurements than other people. Sarah.
I have an online question from Joe Whitty. He's wondering if you could touch a little bit on the effects of ocean acidification on the fishing industry.
Say hi to Joe for me. Say Joe.
Joe! You can say hi right now.
Why don't you say hi to him?
Hi, Joe. Hi, Joe. We'll see you next year, buddy. Ocean acidification is, that's also covered in the report. This is a very big problem because as CO2 levels go up, CO2 dissolves in the ocean, that acidifies the ocean. We're looking at coral reef damage happening today at a rate which is faster than what we think we see in the paleo record anytime, except for maybe a time called the Paleocene-Eocene thermal maximum when we think that large amounts of greenhouse gases came out in a short period of time. At that time, 90-something% of the species in the ocean died off. So ocean acidification is a very real worry. Something on the order, so Tony Barnowski, who was on the committee with us, is an expert on extinctions, and he was talking about something in the neighborhood of 10 to 20% of all of our fisheries globally are dependent on coral reef ecosystems. And that's all at stake.
I got a high back with lots of exclamation points.
Oh, Joe.
Feeling the love.
I'm basking in it. I'm not getting it from the room, by the way. Yeah, Matt.
Matt Safino, KGW. Jim, you just mentioned that you've seen in the paleoclimate record abrupt changes as great as 10 degrees C in the Greenland record. If I were a climate change denier, I would say, see, it happens naturally. So why, again, just to play devil's advocate, why worry about the anthropogenic changes?
All right, so first I got to scratch my head here. What I'm telling you is that the system has thresholds, it has sensitivities. And you're telling me then that's a reason not to worry about it.
I'm saying that I think there are people out there who would interpret what you're saying that way.
No, I understand. I mean, I'm being a little bit facetious here. But the idea that if nature changes, humans can't, that's the logical fallacy in that argument. I've never understood that particular argument. That if nature can change, that humans can't possibly change it. It doesn't matter who puts the CO2 in the atmosphere, whether it's humans or whether it's nature or whether it's an act of God. That is going to warm the planet, okay? We understand from the past, which humans were involved, that CO2 and climate go along together because of the greenhouse effect, right? What that tells us is if we put the CO2 in the atmosphere, we're going to change climate. And really the big difference here is, what I hear when people tell me what you just told me, what I hear is I don't want to take responsibility for what I'm doing. I hear a 2-year-old. Really, isn't that a 2-year-old attitude? I can do whatever the hell I want and I don't have to take responsibility for it. Many people never grow out of that. I work with a whole bunch of them. Yeah.
Jim, Dave Jones, Home Center Communications. The image that you have right behind you there on the monitor, to me, what sticks out like a sore thumb is Greenland. It looks pretty darn red. Could you comment about that and just talk about what kind of trends you're seeing in that area?
Yeah, so this is one of our better ways of monitoring how much ice Greenland is shedding. So, gravity it isn't going to lie to you. This is red not because groundwater is being depleted, but because the ice sheet is disappearing. Or not disappearing, it's shrinking. And so that's why this is red here. So the icy parts of the world, as they melt, show up as less and less gravity because you've got less ice there. You've taken what used to be mass on the ice sheet, you've transferred it to the ocean. Yeah, Sarah.
You had What's some of my favorite and most impactful graphics are the ones that show sea level rise in major cities. So my question is, how quickly can you generate those types of models? Because say if you have a big storm, as we've seen in the past, like a Sandy or one of the other ones that's carved out different parts of the coastline and actually changed the coastline, and we think about Ocean City, Maryland, and those kinds of places that were changed forever by certain storms. How quickly can you regenerate those kinds of model projections and those types of images to affect the new changes to the coastline and how that would impact the cities?
Oh, I would think if the model's good and built well, you could do it very quickly. What changes, so storm surge models are difficult because the bathymetry, and Chris talked about this, is really important. And what storms tend to do is they rearrange not only what you see, but what you don't see below the ocean surface. So you got to basically go out and remap where all the sand got redistributed so that now you have your, but once you have then that base map of ocean bathymetry, that can be pumped into the model with the new bathymetry, and you can generate new storm surge models.
I guess my point is, does that lag of time and that possible expectation change the reaction time for certain cities and governments and civil engineers in actually making changes? If you're talking about 10 years, 20 years down the road based on a current model,
Yeah.
does that argument come up?
No, I don't think so. I think, it's incumbent upon the scientists to be able to provide information in a timely fashion. We can do that if we're provided with the observations or the money to make the observations in a timely fashion. If you say, no, I'm not going to allocate any money to remap the bathymetry of the New York Harbor, we can't give you any better information than we gave you 10 years ago. All right? That's, again, my point. Don't blind yourself. Observe what's going on the planet so that you can make rational decisions about how to triage, what to protect first, what to protect second, what to protect third. Yeah, Ned.
Jim, Ned Gardner, Climate Program Office, and maybe a subtle point, but a surprise in this talk was that you're talking about the boundary conditions, the shifting in human response and the human system responding to the climate system. And I thought the talk was going to be about the natural response shifting quickly. I think that's a really interesting change in the conversation, focusing on the human infrastructure.
Yeah.
And I guess I wanted to just comment on it, and I think that's a great way to shift the conversation.
Well, and that is the difference in this new Academy report, where we looked at this from a human point of view just as much as we looked at it from a natural, physical point of view. Indeed, the conversation today should be about resilience, should be about adaptation. We've got 400 million parts per CO2 in the atmosphere. We're going to have climate change. We're going to have sea level rise. What do we do about it? That's the adult conversation. And what the report does, and we got a lot of press for this, is exactly what you're saying. We said, hey, it's time for us to get serious about dealing with this. We did have conversations with both the Senate and the House staffers about it, so hopefully something will come out of this. We give up?
Jim, one last question. It looks like it's Dave Jones with Storm Center. Last year when we had Jennifer Francis here, she talked about the changes in Arctic sea ice. But one of the questions that came up was, we're adding all the CO2 into the atmosphere, and we're close to 400 parts right now. How come we haven't seen the temperature of the Earth rise just as quickly? And I thought she had a great answer. I thought you might want to comment on that as well, because a lot of people are posting those kind of questions. Mm-hmm. Well, how come the two aren't matched perfectly like we show in some sort of climate record?
Well, I'm no Jennifer Francis. But the simplest answer to that, and I think the best answer, is that we live on a water planet. 70-something% of the Earth's surface is water. So if you warm up the air and you expect the whole planet to respond immediately, you don't understand heat capacity. You don't understand how much energy it takes to warm up water, to cool down water. Try putting a pot of water on the stove. Actually, I tell my class to try this. Put 2 pots of water on the stove, or 2 pots on the stove. One with water, one without. Turn the heat on. Don't do this at home. After 5 minutes, put your finger in the water. It's not very warm. Put your finger in the other pot. It'll burn your finger off. All right? Water. So this creates what's called an intergenerational problem. that whatever happens in terms of forcing functions like greenhouse gases will take 50 to 100 years to express in terms of real climate impact, both in terms of melting ice sheets, warming the water up, everything like that. This is the fundamental intergenerational equity issue. What do we owe our kids? And I love my kids, but, you know, and I think you ask, you know, all of us in our generation, do we love our kids? Yes. Well, how do we show that? Well, we show that by passing off to them all sorts of problems, all sorts of huge economic issues that they're going to have to deal with. And unless they understand that lag, that 50 to 100-year lag, they're going to do exactly the same thing to our grandkids and great-grandkids, et cetera. This is one of those, you know, one of those big fundamental problems where a 4-year cycle of election does not meet the problem, is not an answer to the problem. We got to have people thinking 50 years down the road. We actually have to value our kids.
One more question, Sarah.
I have one more, and I think we could actually wrap it up. This is from Rich Blaustein. He said, if we had a miracle conversion and a national consensus emerged dedicated to keeping parts per million levels to 400 or below, would it be possible, and could we avoid abrupt changes if that happened?
No, and probably no.
On that uplifting note.
And I'll see Rich tomorrow so he can elaborate. Thanks for listening.
Great, thank you very much. Thanks, Jim, very much. That does it for the 2014 Glenn Gerber